Hello, my name is Martin Buchholz. I will present here the Tunisian demonstrator. This is a research project, a part of the EU-funded project Thermochemical Fluids in Greenhouse Farming, so-called TheGreefa. It's funded by the European Union by its program Horizon 2020. I will talk after a short introduction on the components of the system and how they work, and I will finalize with some conclusions. The main objective of this pilot project is to assess the performance of a brine-based liquid desiccant system, a so-called liquid desiccant air conditioning system, LDAS, also called LDAS, used for greenhouse air conditioning. The investigation focuses on evaluating the efficiency of the LDAS in creating a balanced and controlled climate within the greenhouse under Tunisia's climate conditions. The LDAS system is implemented and tested in an innovative water cycling greenhouse, which is characterized by an accordion-shaped design to collect the maximum amount of condensed water. In this system, we are looking at 3 points. One is the air conditioning, the cooling of the greenhouse. Second is the accumulation of CO2 in the greenhouse. And the third point is recycling of water. The desiccant climate control is based on a day-night thermal heat accumulation. That means we are heating a storage during daytime and we release the heat back to the greenhouse during night. The accumulation of CO2 in the closed atmosphere, this means we have a closed greenhouse with no air exchange from outside, will allow to accumulate CO2 to a level of 1000 to up to 2000 ppm. This is 2 up until 5 times more than in the normal atmosphere. And this will allow improved photosynthesis. If other growth factors like water, nutrients, or especially light are satisfied, then the CO2 becomes a limiting factor. And if we also generate here an optimum, we have more growth. This means improved production. This is not possible in an open or semi-closed greenhouse, where normally CO2 added to the atmosphere is aerated outside, and you will never reach these levels of concentration and you will lose a lot of CO2 supplied. But the improved CO2 level also relates to a improved heat acceptance of the crops. It allows less cooling measures, so the crops will also have a sufficient CO2 supply even at closed stomatas, which are normally resulting of heat and water stress. So this means more CO2 also relates to less cooling efforts. Then the final goal is the water recovery by the combined evapocondensation. So we have water gained from air humidity to the desiccant during daytime, while the water from the desiccant is redistributed to the air during nighttime using the heat from the storage. In that period, we have condensation of water at the inner surface of the foil. A removal of water droplets is gained by modified roof shape, providing sufficient slope for droplet removal and collection. In a normal tunnel greenhouse, the drops would just drop from the roof back to the crops and will cause some harm to the crops, while with this shape we can collect the water in a tank. Heat removal by modified roof shape is also a by effect. So the zigzag shape of the greenhouse provides a larger surface, which also can remove more heat from the greenhouse. On this slide, on the left, you see the zigzag shape or accordion shape of the greenhouse on the left. And on the right, you have all the components. So we have the yellow colored greenhouse with the blue absorbers on the top. And on the left, we have the storage tanks with the desiccant. And we have circulation with the desiccant between the greenhouse and the tanks. And we have circulation of air between the absorbers and the greenhouse envelope. Here are some details of this new shape. And you can imagine that, let's say this greenhouse has a length of 12 meters, but once it is properly working, it can be increased from 12 meter to 1200 meter, like any tunnel greenhouse. And by this, we have an upscaling possibility, which is quite easy. On this slide, you see a photo of the demonstrator. And on the photo below, you see a 1 cubic meter tank. This is a combined tank collecting rainwater from the rooftop and also collecting the condensed water droplets from the inner surface of the greenhouse foil. The absorber is the main component of the greenhouse air conditioning system, ensuring the circulation in counterflow of the brine solution and the air drawn from the greenhouse. This circulation allows the regulation of both air temperature and humidity by converting latent heat into sensible heat while absorbing air humidity. The absorber was manufactured by the working group of Technical University of Berlin and WaterG. Initial tests of the absorber prototype did provide clear information on deficits in liquid distribution. Infrared analysis, seen on the left figure, showed that heat release in the running process is unequal due to different flow rates in the center with low flow and perimeter of the absorber with high flow. By using a colored liquid, also problems of unequal distribution was demonstrated. You see it in the middle photo. Deficits shown by the tests did result in a new design of absorbers shown on the next slide. Unequal distribution of air in the bottom of the absorber was shown by fog analysis. The air was mainly led to the top from an area near to the air entry due to a dense configuration of absorber elements. A new design provided a shape of absorber elements with decreasing diameter towards the bottom, allowing air to enter into the inner area of the volume. The new design for the absorber desiccant distribution element is aimed at a total decentralized supply of liquid between the hexagonal openings you can see on the middle photo. A central desiccant inlet on the bottom, which you can see on the left photo, is connected to a system of internal channels in the printed part, driving the fluid to plenty of small openings between the hexagonal openings. This allows a very equal distribution also at high flow rates. This slide is describing the testing of the performance of the desiccant. The operation of the absorber device of the system is based on the hygroscopic properties of the TCF, the thermochemical fluid used, which is a brine solution of magnesium chloride, which is available in Tunisia from the existing salt works producing sodium chloride from seawater. It is a byproduct from those salinas. The measurements of the equilibrium relative humidity were performed during January 22 according to the saturated salt solution method that involves placing a sample of the brine solution in a sealed container and measuring the relative humidity of air in contact with the BLD, the liquid desiccant. When air reaches equilibrium with the desiccant, its relative humidity corresponds to the equilibrium relative humidity of the desiccant fluid. On this picture you see the measurements of these tests. So the yellow curve shows the desiccant, which is at low relative humidity. The purple curve shows the relative humidity in a other container just containing water. So you see it has a very high relative humidity as the water air is the air above the water, of course, is saturated almost. And the curve between the blue one is showing the relative humidity in the greenhouse, which is the surrounding of these two containers. Now we describe the desiccant circulation in the system. Two interconnected storage tanks with a total volume of 15 meter cube of the brine solution were utilized in the studied system. The storage tanks are connected to the absorber device via two pumps of a hydraulic setup. The absorber devices were mounted on stands at a higher level than the storage tanks in order to allow the return of the fluid solution by gravity and to reduce the complexity of the system's control. In this way, we only need pumps from the storage to the absorber, but we don't need pumps for the return. Air is drawn from the greenhouse roof and conveyed through the absorber. After undergoing thermal heat exchange and the dehumidification, or in the nighttime humidification process, the processed air is blown into the greenhouse at the level of the plants. On the photo you see the two absorbers in the background of the photo and on the right photo. And in the left and the right side of the photo you see the air distribution pipes, which are providing the treated air, the more drier and cooler air, back to the vegetation area. In the system we have involved a monitoring system, so we can control the whole parts of the system by a control computer. So the control of the desiccant system is run according to 3 stages of intensity in day and night mode. We have the first mode, which is only run by one pump, a second mode run by a second larger pump, and a third mode where both pumps are running all together. We are also measuring the system, and we are measuring temperature and relative humidity at different areas of the system. We are measuring the desiccant flow rate and the airflow rate, the CO2 concentration, and the desiccant level inside the storage tanks. With these parameters we can calculate an energy balance, and by this can see how the cooling and regeneration functions of the systems are working. We had a tomato production in the system in 2023 and 2024. So here you see the seeding of the plantation. This was done in open mode, and the first harvest in April 24 with a production of 200 kilos. This was run partially in open mode and partially in the closed mode as described in the photos before. Here are some conclusions and learnings from these tests. We need a high level of airtightness in the greenhouse. It's needed to reach condensation conditions. An error-friendly emergency ventilation is required, but it needs to support the concept of tightness. The installation of the absorbers in the greenhouse has to be done, and was compared with the placement outside of the greenhouse, which was much more difficult. So an installation inside of the greenhouse is recommended. The absorber design was a successful design aimed at the reduction of complexity and costs. This is important to reach a market entry also in countries like Tunisia. 3D printed parts for the experiments require high quality, heat-resistant plastics and require sun shield to prevent overheating. This is not important for the final functioning of such a system, but for the experiments. The storage volume is expensive and hydraulic connections are error-prone. This is a main focus of further improvements. Desiccants need high attention concerning corrosivity, leakage, disposal, and recycling. What are the next steps? The use of PCM, phase change materials, can be considered for heat storage and shall be further investigated. It will allow a reduction of desiccant quantity and storage tank quantity by 50 to up to 90%. An integration of PCM placed within the absorber may also reduce pumping costs by around 50 to even 90%, and also will allow a slight reduction of ventilation requirements. All this is important to reduce the electric energy requirements of the system and to make it marketable. Low-cost PCM materials for a melting point around 30 degrees would be required. Candidates for such a material could be chip fat or sodium carbonate. These are examples. A further simplification of the zigzag construction is possible. Finally, it will be not much more expensive than existing tunnel greenhouses. Further research activities are required to establish such a system, also due to a lack of alternatives for overcoming the water crisis. There were actually high recent activities in building air conditioning using liquid desiccants. Startup companies like Blue Frontier, funded by Bill Gates, and 7AC are recent multi-million investments in LDEC technology. So there is a lot of competition remaining in this part of the research, not only for greenhouses. Thank you for your attention.